Hello everyone, this is Mr. Woodward. In this video I'm going to show you two examples of some more advanced kinematic equation problems. Let's take a look at this first example. Sarah is approaching a stoplight, moving with a velocity of 30 meters per second. The light turns yellow and Sarah applies the brakes and skids to a stop. If Sarah's acceleration is negative 8 meters per second squared, then determine the displacement of the car during the skidding process. So we're going to start over here with some givens. And in the givens column, I can pull out already some very obvious ones. So here we go, velocity of 30 meters per second. So this is her initial velocity. I'm gonna change my pen size just a little bit. 30 meters per second. And then I've got another really obvious one here, acceleration of negative 8 meters per second squared. And it says determine the displacement of the car. So my unknown is displacement, right? Delta x. But if I'm careful, I can actually read closely and see that there is a hidden given, which is that Sarah applies the brakes and skids to a stop. So that's her final velocity. Coming to a stop means the final velocity is 0 meters per second. So again, like always, I'm going to look at my givens and my unknown and try to find one of the big three equations that really relates all of those together in one spot. And equation 3 does this nicely because equation 3 looks like this. It has all of these components, including the unknown. So I'm going to plug in some numbers and see if I can do the algebra. The final velocity is 0. The initial velocity is 30 meters per second. I'm going to square that. 2 times the acceleration, I've got my negative 8 meters per second squared, and then times delta x. So in simplifying this, this is going to go to 0. This is going to be 900, and I can apply the square to the units as well. So it would be meters squared per second squared. This is going to be minus 16 meters per second squared, and then times my delta x. So I'm going to pull the 900 over to the left side, subtracting this from both sides, minus 900 meters squared per second squared. Means I have negative 900 meters squared per second squared is equal to negative 16 meters per second squared times delta x. My next move is going to be, I've got to isolate delta x. So now I'm going to divide both sides by negative 16 meters per second squared. Divide this by negative 16 meters per second squared. So the units cancel partially. Meters go away. Sorry, they fully cancel here. But second squared in the bottom of both of these, and then meters squared on top. So one of the meters goes away, and the meter on the bottom goes away. So I'm left with a unit of meters. So delta x is simply going to be equal to negative 900 divided by negative 16, which gives me 56.25 and then meters, because those were the units I was left in. Now, this was a what I would call a numbers first approach, meaning I immediately plugged in all the numbers and then solved for delta x. You can also do a letters first or variables first approach and manipulate the variables first and then plug everything in at the end. And I'll show you how that works. So let me get rid of this. So what happens if I do the algebra first? So if I do the algebra first, I want to isolate delta x. So my first move is going to be to subtract v initial squared from both sides. So I would get v final minus v initial squared is equal to 2a delta x. And then to isolate delta x, I would divide both sides by 2a. And so I see that, so these will cancel. And so I'll get delta x all by itself. So I'm just going to flip it around and say delta x is therefore equal to v final squared minus v initial squared divided by 2a. Now that I have the equation manipulated, solving for delta x by itself, I can start to plug in my numbers. And so here I'll just do it in one swoop. V final is 0. V initial is 30 meters per second. I'm going to square that. And then the acceleration is negative 8 meters per second squared. And so I can just, so this goes away, right? So it's just going to be 30 squared and the negative of that, so there's my negative 900, divided by 2 times negative 8, which is negative 16 in the bottom. So my units cancel just as they did before. So I've got seconds squared on top, seconds squared on the bottom, those go away. And then meters squared on the top will cancel with this meters, and it'll leave one of these all by itself. So I'll end up getting the same answer, 56.25 meters. So again, just two approaches, either plugging in the numbers first or manipulating the variables first. In this case, manipulating the variables first ended up using a little bit less space and was a bit more efficient. So either way is fine. Let's try example 2. I'm going to clear a little bit of this away. Joe is waiting at a stoplight when it finally turns green. He accelerates from rest at a rate of 6 meters per second squared for 4.10 seconds. Determine the displacement of Joe's car during this time period, so while he's accelerating. So here we go. We've got some obvious ones. We've got, right, he accelerates at a rate of 6 meters per second squared, so that's easy. Can easily include that one. I've got this 4.10 seconds. That's clearly a time. And then my unknown is, again, displacement. But there is another hidden given in this particular problem, and it's right here. It says he accelerates from rest. From rest means that Joe's initial velocity was 0. Okay? So I'm going to look at my givens and my unknown, try to identify one of the big 3 equations that relates those together. And equation 1 is going to do this nicely, which is that delta x equals 1/2 at squared plus v initial times t. And you don't have to say the dot. It's just v initial times t is fine. So this one is already nicely solved for delta x. So, right, the unknown is already there. So I don't have to do any algebraic manipulation. I can go ahead and just start plugging in my numbers. So let's try it out. 1/2, the acceleration is 6 meters per second squared. The time is 4.10 seconds. Square that. The initial velocity is 0. The time is 4.10 seconds. But of course, 0 times anything is just 0, so that whole term goes away. And so this gives me 50.43 meters. And then let's take a look at the units. So seconds squared over here is going to cancel with seconds squared here because this is in the denominator. So these will go away, and we will be left with meters uncanceled. So that's why we get meters here, which makes sense because the answer is asking for a displacement, and we would expect the displacement to be in the unit of meters.